Welcome, everybody. I'm Dave Sellinger, and together with a number of the folks on here, we host this every single week to talk about AI and machine learning and papers, and it's not quite as intense as the one that Ted runs down in San Diego, but we do like to cover kind of bleeding edge topics and try to bring it back to my approach in this is always to bring it back to fundamentals as much as possible, because I find that just repeatedly understanding the underlying fundamentals of these things is the strongest basis from which we can understand each of the problems. A couple of quick rules about participation: ask any question that you want, stop us anytime you want. If you ask a dumb question, that's your fault. But we always welcome all types of questions, and there's no such thing as a dumb question. So if anything, right, it gives us an opportunity to go back to the fundamentals and understand something better. I find that the number one principle, and the reason I started this group like 6 or 7 years ago, was that the act of answering someone's question, or at worst, trying to answer someone's question, is the best way to learn yourself. Teaching is one of the best methods for doing this. And so I'm going to be presenting a paper called Perfusion, and I've done my best to understand that, but I guarantee you I've done stuff wrong. And again, the reason we started this group is to find those things together and create a safe place, if you will, to really tackle some of the most advanced topics out there and learn them together. And it's been, for me, one of the highlights of my last 6 years. In fact, throughout COVID, there are a number of people on here that were on here through COVID. We used to meet face to face before, and this is definitely was the thing that kept us alive through the pandemic for a lot of us. So with that, I'll go ahead and get started. I think Chulin, we've met you before. Pushpa, did you want to introduce yourself anyway, since I haven't met you yet? And
yeah, sure. So I just started. So I work at Walmart Labs. And just started working on computer vision. Before that, I was more working in traditional machine learning field. But before that, I'm a PhD in material science, physics to be specific. Yeah.
I love material science. That is one of my favorite topics in the universe.
Yeah.
In fact, yeah, I'll talk to you offline. I have a friend who runs a material science company, and he's been looking for someone to help advise him on data science and stuff. So, Herline, looks like you're on here a couple times. Did you want to introduce yourself and say hi real quick?
Hi, my name is Herline. I'm joining from Montreal, Canada, and my background is mainly in computer vision. Yeah. Thanks.
Awesome. The regular folks, Ted, Jerry, Dave, and Roger.
Yeah, I can say hi. Hello from San Diego. My name is Ted Key. I work primarily in healthcare, but I would say that my ML interests are really across the board at this point.
Hi, this is Dave. I live in Pleasanton, same town as Sally, and been part of this meetup for around 5 years, or at least 4 years. And I can say that this is the best thing that has happened to me in the last 4 years.
Thanks, man.
And I've learned a lot, and I've pivoted a lot, and you know, as Sally said, I've misinformed everyone a lot, but learned a lot along the way.
Hey, Dev is the one who caught Transformers before anybody else, so mad props to Dave for that. Jerry, and then Roger.
Hi, I'm Jerry Karata. I'm based in Pleasanton also. We all used to go down to Dave's office in downtown and sit around the big table, and I think we had
Pizza.
a little track for
Every once in a while.
Eat pizza every once in a while. Had a little track where we had a little car run around and things like that. So this group is just super. Right? No question is too dumb, which is good for me because I ask good questions. So it's just a lot of fun. So I hope everybody enjoys it.
And hi, I'm Roger. I'm kind of the traveling member of the group, currently calling in from Philadelphia. So it's a little later here for me. My career was more in software storage in particular, and I'm just a recreational machine learning enthusiast, and been at this for what is it now? 4 years, 5 years, something like that. So it's learned everything from this meetup, and it's been great.
Awesome. And then Shulin is going to be a speaker for us in 2 weeks. Woo!
Hi, my name is Julin Han. I'm actually also in material science and engineering. I'm currently pursuing my PhD degree, so funky journey. I'm currently doing I'm trying to explore machine learning and AI techniques in semiconductor modeling and nanomaterial modeling. So yeah, so nice to meet you.
Great, thank you. So with that, I will I'll just put one more pitch in. If I do have a topic, Shulin is a newer member of the group and has volunteered to give a presentation in a couple of weeks. Everybody is welcome to help us read a paper. The only commitment that we have is take the time to read it in advance, come up with some questions. If you want, prepare some slides. If you can find example code, things like that. With that, I'll go ahead and kick us off. We have an agenda. I think we have an issue with the agenda next week, Dave. Is that right with you? Potentially?
Yeah, I potentially will have an issue as I reached out to you separately. So, I mean, I can still try to do the video, but you know, it's I don't want to just do a video and not talk about it. So,
do your best. If you can't do it, then we can all pitch in.
More
and we'll
confident
do it.
of the week after next as of now. Things should hopefully settle down.
Just keep us posted how it's going. I'm like I said, I'm going through almost something like I literally took my kid out of school 2 weeks ago, or a week ago, sorry. And we only went back to school a week and a half ago. So, all right. So with that, I will go ahead and start our discussion on perfusion. I will click both of the optimize buttons here. Can you guys see my slides here? Okay. For those of you who are not familiar with it, this is Microsoft's browser. It's rad.
Yep.
I'm not usually the biggest fan of Microsoft stuff, but I think their browser is really, really good. I'm so impressed that they've adopted open source more than I expected. So I do use Microsoft's browser here. So we're going to talk about Perfusion. And Perfusion is kind of interesting because Nvidia had this big announcement where they made one of those claims that reminded me of room temperature fusion or room temperature superconductors. And it was just such a big claim. They've beaten the state of the art by 5 orders of magnitude. And so what I would highlight here, just to temper everyone's expectations, they have certainly accomplished a 3 or 4 or maybe 5 order of magnitude improvement on certain elements of the way that they have solved the problem. It is not a model that is 5 orders of magnitude smaller than the state of the art. So if you came here expecting room temperature fusion, it is time to log out because I will not share that with you. That said, it's really cool. It is a really neat model. It builds off of a lot of the topics that we've covered in the last 6 months. It builds off of Rome. It builds off of kind of the parallel modeling approaches. It's got some neat buildups. So for the agenda, as I mentioned, I love to do fundamentals first, just because I think it helps us get us all on the same page as we approach the problem. So I'm going to spend a little bit of time on LLMs, and it'll help us kind of just align on some of the problems that we're solving, why we're solving them, what are some of the key blocks that we're using. I may even, if people want to, I prepared a video that we can watch together covering that, which would extend it more into like a 5-minute, 10-minute primer. And that includes also attentions and transformers. Diffusion model is the other key piece of background. I am not going to do a backgrounder on Rome, though actually I think a backgrounder on Rome would be the most useful thing, but I wasn't find anything that gives a backgrounder on Rome in less than an hour and a half. And if I recall correctly, when we covered Rome as a paper, we spent 3 weeks on it, if I'm not mistaken. I think that was you, Dave, and you, Ted, is that right?
Yeah, I remember doing Rome. I still have some funky attention diagrams from that.
Yeah. So I would love help from you guys, just because we're going to get to a section that like runs headfirst into Rome. If you haven't read the paper, the key contribution here is essentially applying this technology called Rome and modifying it in a bunch of different ways. So first off, as a background of what's an LLM, an LLM, it's like ChatGPT and everything in the world, is a feed-forward neural network that performs natural language tasks, and it's expanded to the text from text to image problems, image generation, and it's really an impressive chunk of work. What we again, what I give credit to Dave for is bringing to us the secret sauce of LLMs. It was originally put forward in a paper called "Attention is All You Need," and to kind of give some background on what attention is. Attention was originally developed to solve natural language problems that were currently being solved by a thing called recurrent neural networks, or LSTMs, long-term short-term memory models, which again was a form of a recurrent network. And what a recurrent network did is it digested a sentence or a string of characters or a string of tokens one at a time, recursively digesting each of those elements of it. And then again, probably using, in the case that we were analyzing it, some sort of a feed-forward multi-layer perceptron network. There were certain structures of that, like a memory, which was an LSTM. But in the context of attention, what attention did was it said, instead of digesting data only sequentially, let's give ourselves the ability to look either forward or backwards with particular interest at particular tokens relative to where I am right now. So if I said the dog ran forward and it tripped, being able to digest the word "it," which is a pronoun that has the antecedent, which we know as human beings was the dog, is a very challenging thing for a recurrent neural network, because it can only hold kind of this state thing, a generic state or a generic memory, and refer back to that. It doesn't know where that came from. Whereas what's actually important in processing a lot of problems is knowing exactly where you're looking. I'm going to look backwards 2 tokens or 3 tokens for the thing that is going to tell me what it is. It's a dog in this particular case. And to solve that problem, they created a specific type of a neural network block called a transformer. And we're going to be dealing with a transformer, and the way to kind of think about that is that a transformer is a way to direct attention in a way that is aware of its context. So in this particular sentence, I want to look back 2 tokens. In this other sentence, I want to look back 5 tokens. And maybe for solving a different problem, even though I'm in this sentence where I would normally look back 5, I also want to inform it by, let's say, six tokens back and see if there's maybe a color or a modifier. And so those would be what would be called a multi-head attention. And then cross attention, sorry, the first 2 things I described were self-attention, and multi-head attention would look at multiple areas. And then cross attention would, instead of be looking at one area, looking at another thing for either the context or for the area of applying the attention. The transformer architecture and block is reasonably standardized and is really kind of the centerpiece building block of all of the large language models that we're looking for. Anything that I said that's wrong or needs addition there from anybody there?
I think you got it.
If you don't mind, I'll give another example for the cross attention.
Of course, please.
So the attention is all you need paper, the first place where people were using this was actually in translation. And so let's say you input French and you want to output English. So where cross attention would come into play, for example, is you're outputting what's the classic sentence, je suis étudiant or whatever, like, and then in English you're saying I'm a student. So you need self-attention when you say I am, and then what's the next word? Well, you need to know that the first 2 words you already said are I and am, so that you know kind of what word to say next. But you also can do this cross-attention thing where you say, I'm going to compare myself to the French sentence to know what concept should come next. So you're combining two different things. You're looking at where you are in your sentence, and then cross-attention is where you're looking at something else instead of comparing to yourself.
Thank you. Perfect example. In fact, a great segue even to the next slide, which is talking about the problem of image generation from text. And in the problem of image generation from text, you do need to know exactly what Ted just said. You need to know both the self-attention, which would be from the text, as well as what are the pixels that are in my output that I'm going to be generating. And in fact, when you look at the way that image generation from text has gone, there are two kind of key concepts that we have to bring into this problem. And these are, for example, the all seen DALL-E generating these really cool images here, or Midjourney, which is also doing the same thing, generating images, but they actually take a different approach. They use the two kind of primary building blocks here slightly differently. And what I'm going to basically look at it as the first problem here. Should I zoom in? Well, if you can't read it, it says a corgi playing a flame-throwing trumpet. And this is the example actually from the DALL-E 2 paper. And the first thing that you have to do is you have to understand the sentence. And that's where this self-attention and multi-head attention and cross-attention model comes into play, is being able to create an embedding not only of the words that this says, but actually creating effectively a diffuse embedding space of what the image might look like that does this thing. An image of a corgi playing a flame-throwing trumpet. And so I'm going to zoom in on this model specifically, and there's a secret sauce that's in both of these that also has been added when we move from the space of just NLP into image generation, which is this thing called diffusion. And if you've been following the space, you've heard the term stable diffusion. And if you look at this block right here is what was put right here in the DALL-E paper. It's used also in the Midjourney paper in that it's kind of represented here in the noise edition. But what I wanted to do before we go into the particulars of Perfusion was spend 5 minutes and watch just a primer on diffusion, because it's kind of the process that Perfusion is modifying. It's taking this standard stable diffusion process and it's tweaking it a little bit. So if it's okay, I'd love to kind of talk just for 5 minutes about how diffusion models work. And I found a little video that's really great at explaining that. But the high level of the way a diffusion model works is that you basically march forward. You take a set of images in a self-supervised model, which I think is rad, by the way, because self-supervised basically means unbounded data. You don't need labels. Diffusion models are some of the first. One of the neat things about image from text is that it uses the two approaches that are both self-supervised, which I think is the first time in all this deep learning revolution, if you will, over the last 8 years. Everybody says it's because there's all this data, and then you actually look at the data set, it's like tens of thousands of images, and which is kind of horse crap, right? Like that's not really taking advantage of all the data that is in this huge internet. Stable diffusion and image generation does, because the natural language problems that we're solving, going back to this first slide, text classification, you can't do that without having labels, but gap filling and question answer, you can. And so they were able to do some of the initial training using entirely self-labeled, self-supervised learning, which is what enabled these models to not only be very accurate because of the architecture, but also because of the way that they formulated the data problems, which I think is also really cool. Diffusion models do the same thing. Diffusion models take any image that you say, this is a good image, and it creates its own training data. And its own training data is sampled from Bayesian noise. Yay! So like, okay, so how do you do that? How do you actually use Bayesian noise as training data? Well, it's not the beginning or the end that matter. It's actually these transitions. It breaks it down into these steps where you progressively take this image of is that a lab, a pretty dog, and then you progressively noise it in order to predict what would it take for me to move backwards. So as I create this sequence of adding noise, I've actually created the training data to figure out how do I reduce noise. If I were to start out with this as my input, how would I generate an image that's awesome like this from it? And essentially because this is Bayesian, not Bayesian, sorry, it's normal noise sampled from a normal distribution, then I should theoretically be able to create anything from noise. And so I'm going to take a second and actually play a video on that, unless anybody wants me to pause before I do that. Okay. If you haven't seen this video, it is awesome. It goes through all 4 levels. It starts at basics, boom, boom, boom. I'm just going to show level 4.
Let's learn about
because that's going to be what we have time for in order to progress through the paper.
Level 4. We learned what it means to add the noise, but what does it mean to reverse or remove this noise? Reversing or removing the noise means recovering the values of these pixels so that the resulting image will resemble the original image. In diffusion models, this is achieved by using neural networks. So let's look at our 2-pixel example again. Let's say this is where the image lives, and this is the point. It is fully noise. During the forward diffusion process, the image follows a path from the original position to Gaussian noise position. During the reverse diffusion, we want to find a way to bring it back to its original position. To do that, we input the image to a convolutional neural network, and we ask the network to produce the image in the previous step. The type of convolutional network used in the original paper is called a U-net. It is called that because of its shape. Through the convolutions, it makes a small representation of the image and then upsamples it back to the original dimensions. This way, the input and output dimensions of the network has the same size. Okay, that was a lot of information. I hope you were able to follow along. I based this video on this amazing article made by my colleague Ryan O'Connor in the Assembly AI team. And on top of everything we learned here today, the article goes deeper into the math.
So I'll pause there. If anyone wants to do a longer explainer on that, but I thought that was just a great kind of 2-minute way of this illustration. I thought was awesome at capturing. These 2 illustrations were awesome at capturing kind of what a diffusion network does. And when you think about text to image, what you effectively want to do is every step along the way, as you're going from Gaussian noise towards an image, you want to make sure that either you've started with the Gaussian noise that fully embeds the information of your image. So in this noise is the sentence, a corgi playing a flame-throwing trumpet. Like, it doesn't look like it's in there, but actually that's exactly what this chunk of noise says. We've embedded all that information into that. That's one way to solve this problem. The other way to solve this problem is to make sure that every step along the way, as we're going from here to here, every step is getting closer and closer to something that looks like a corgi. Is it a corgi playing a flame-throwing trumpet? Is that what it is? Yeah, it is. A corgi playing a flame-throwing trumpet. And so you effectively have 2 kind of ways to influence this model as you move forward. Again, one is embedding all the information of your sentence into the noise, and the other is to modify the path forward from the noise. Is that, am I on point so far? Okay.
Yeah, that's great. Can I just share a teeny bit of history? So the first diffusion model, I don't know exactly if this is it, but like, let's say you trained it on all these ImageNet images. And if you know ImageNet, it's got 1,000 different classes. Okay, so the neural network learned how to reverse that noise process, but it really only learned it for those 1,000 things. Okay, so when you started out with just noise, you're going to get a rose or a corgi or whatever one of those 1,000 things. You're never, like, let's just say hypothetically surfboard was not one of the 1,000. You're never going to get a surfboard. Okay, but you will randomly get a very realistic looking image from one of those 1,000 classes. So then the next thing people said was, wouldn't it be nice if I could pick which of those 1,000 I wanted? And so you say, I want a corgi. And so then they figured out a way to kind of given an input, which of those 1,000 classes, and put their thumb on the scale, so that then when it was denoising, it would denoise only in the direction of corgis, and you wouldn't wind up with a German Shepherd, and you wouldn't wind up with a cat, you wouldn't wind up with a rose. So then the next huge step was, wouldn't it be nice if instead of just like one of these 1,000 classes, I could just tell it what I want? And that's what ultimately people got to with Stable Diffusion, Midjourney, DALL-E 2 is now instead of just a number 1 through 1,000, you actually can do what Sally said, where you run it through the text model, and you have to figure out, how do I then take that information and apply it to this diffusion model, right? Like, I have this embedding, these numbers that mean a corgi playing a flame-throwing trumpet, but even though those numbers mean that, how does my image model know that that's what I'm supposed to do?
Cool, thank you. And that's another great segue to kind of the way I'll talk about what the contribution is here, which is, and contrast it with what it is not again. But so what the problem that Perfusion aims to solve is essentially, now we've got these great models that can take text of any form, digest them, embed the meanings of the tokens, then embedded that meaning either into the process or into the noise that we then denoise to create our image. Now I want to inject my own images. Like, hey, I've got this really cute teddy. I want this. When I say teddy, this is what I mean by teddy. It is this guy right here, and he is Teddy. No matter what you do, if I give you a sentence, I want Teddy dressed like or Teddy dressed in a blue suit. That's what I want coming out. Teddy sitting in a fire. Teddy, and if you said Ted instead from the movie, right, then he'd be peeing in a urinal, right? But this is Teddy instead. Teapot, again, here's what I want to make sure that I have a teapot made out of pure gold, glass, yarn, oil painted, Ghibli inspired. Holy crap, like how cool is that? But you're able to essentially, with a few examples of data, which is a type of learning called few shot, personalize the output. Now, are you personalizing the model? Are you personalizing the process? Are you personalizing something after the fact? Or are you personalizing the embedding at the beginning? That's effectively the question that we're trying to answer with Perfusion. How do I inject into this process my own personal bias and I'm going to use the word bias on purpose here, by the way, for those of you that caught that, so that I can capture and put that object into my my text to image problem. So here's the opener, and I had to show this just because, I mean, my God, we always joke about like academic papers and the level of self-affirming language that is used, but I've never seen anybody go for 5 orders of magnitude on the first page. These guys just own it, right? I mean, they didn't F around. They've all these videos and they're pretty ridiculous. But anyway, what they claim is that it's a 100 kilobyte model that takes 4 minutes to train, and it has these 2 kind of core mechanisms. One is called key locking, key locked rank 1 editing. And the second is the modification to the rank 1 editing. And so I'm gonna go ahead and show you a video now about introducing this. These are more kind of in the space of, this one's history, no math is what I'll call it. The next one is history with no math but diagrams, and then we'll go through the paper. Okay.
Hey, Sally.
Yes, sir.
Sally, can I ask just a quick clarifying question before we dive through it? In the examples that you showed, it looked like the examples were associating an image of an object with a word, and then the production, the generation side would use that word, and that picture of that object was kind of injected in both of those examples. So is that what this does, or is there?
That is what this does. That is the problem.
Oh, okay.
So the problem they're solving is not text to image in a 100 kilobyte model, which is what this sounds like. It kind of says, but there's this word right here, personalization method.
Right.
So if we were to write an attention-based model to analyze this, it would have done what we all did, which is breeze over that freaking word and keep going. Whereas the actual map of this entire page should be that word and everything else doesn't matter.
Right. Okay. And then how about like style? Image style, is that something they do as well? Or is it just
No, it
this
is
take a noun and
object
create
embedded.
an image for a noun?
Or sorry,
Okay.
not object embedded. Object entity creation.
Gotcha.
So
yes.
yeah, so the simple use case is you're using vanilla text to image, whatever your preference, Midjourney, whatever, right? And you're like, hey, I want a cute teddy bear who's a knight in shining armor or whatever, okay? And like you go through a bunch of different seeds and you work on your prompt and you do 1,000 of these and you finally find one. You're like, this is perfect. This, like, my daughter, if I do a bedtime story with this teddy, is gonna love it. Okay. Now I got this one image. Okay. Now page 2 of my bedtime story. The knight is riding a horse. Well, you put teddy bear knight riding a horse and you get a completely different looking teddy bear. Like,
That's
no,
right,
this
yeah.
isn't gonna work. It has to be the same teddy bear.
I need it to be angry
Right.
cat. I want angry cat in everything. And so
Yes.
you can give it that a couple of examples. And again, this is that few shot bit. You'll need a couple samples, and then you can put Harrison Ford back into the Solo movie, right?
So the main use case, the main use case is now that you have a main character, you just want consistency of that identity in future images that you generate. And then if you want a different character, then you don't use that. Then you say, okay, fine, now I want a monkey to appear in my story. So you don't use this Nvidia thing. You find a monkey you like.
And kind of go back and reread this sentence with that highlighting, which is thank you, Roger. If you reread this page with that highlighting, not only does this make more sense, but the contribution makes a lot more sense, right? It's like we're solving this personalization method where the model for personalization is only 100 kilobytes. The model for personalization only takes a few minutes to train, and it can still solve that, leveraging the quality, breadth, and stylistic capabilities of the underlying LLM that's used, whether that's DALL-E or Midjourney.
Okay.
Yep.
And I see they say personalized objects. So it is specifically
Yeah,
objects.
it's just be one of those things where you would kind of wish that they would be more crisp, right, about like what is the actual contribution. But again, it's still cool. I don't want to put it down. It's just when you read the summaries, you're like, holy crap, the world changed. We now have a 100 kilobyte LLM that's trained in 4 minutes. There's not ludicrous, right? So you got to read it a couple times to get that. So here, let me go ahead and show you guys.
Dear fellow Scott.
Oh, sorry, you got it from this kid here. Okay.
2-minute papers with Dr. Károly Zsolnai Fehér. Today, we are going to have a look at an image creation AI called Perfusion that is completely out of this world. Imagine a text-to-image AI like Stable Diffusion or Midjourney as a chef that can cook any dish. However, sometimes we like the dish we get, but we would like to introduce our own ingredients to it. And normally, if we write a new recipe, a new text prompt, we get a completely new image, a new dish. However, that is not what we want. What we want is the previous dish with a new ingredient. Let's have a look at an example. We have photos of our favorite teddy bear, and we would like it to create an image of it playing with a ball in the water. A previous technique does... I have already looked at this image, and I have bad news. It's not going to be pretty. Are you ready? Okay, here you go. Whoa! It seems to have fallen apart, and there is no ball anywhere to be seen. Now, let's look at the new technique. Now that's what I call a great result.
There's a little bit of a hint here about how it's getting done. I'm just gonna point it that he doesn't mention it, but this is the heat map that is the key locking component. The key refers to where in the model where in the output am I influencing it using my special term, Teddy. in this case. And you're seeing that in the historical models, it's pretty diffuse, right? So that key, the location where Teddy is being projected into this image, or in-painted, I guess is the right term, is pretty diffuse. Whereas when you look at the output from this model, it's not very diffuse. It's very pronounced that the Teddy with the ball is right here. Okay.
Now that's what I call a great result. Love it. However, this is an emerging research field, so of course, this is not the only previous technique out there. Let's take this adorable cat. Yes, this cat is missing a pair of headphones. So let's add it with another previous technique and nothing. Look, at least I see the remnants of some crazy thoughts this earlier AI has about headphones. It sees them more as yo-yos. Now, the new technique. Oh yes, fantastic! And of course, the new technique knows that you can never wear enough headphones, so there we go. So cool. So, this new paper finally enables this kind of personalization with something that they call concepts. What is that? That is the AI chef's cookbook. Having a teddy bear dressed like a wizard can be a concept, a sombrero can be a concept, all of these can be concepts. And here come 4 incredible kickers. 1, as many of you fellow scholars know, some people like pineapple on their pizzas. And some people like eggs on their pizzas. Well, here is the kicker. It can fuse concepts together as well. This is an AI that can make that pizza happen with pineapple and eggs at the same time, but without sacrificing the quality of the food.
So this is an important concept as well. I don't think that was a great example, but this image is a great example where you're asking a model that generates pizza, let's say never puts pineapple or eggs on them, it doesn't even know what those are. You create this named entity called a pineapple, a concept called a pineapple, and you create a concept called an egg, and you train it on that, then it would be able to combine the two. One of the other problems with the prior personalization techniques is because of this diffuse nature of them and some other issues with the way that they're trained, they cannot combine concepts. You can't train it both on Teddy and on something else. So he doesn't show good examples here. I was kind of bummed about that. But this image here was good at showing eggs and pineapple together.
A huge challenge.
So Sally,
let's have a look. First, take...
Yes, sir.
Oh, I was just going to say, and then this may come later, it talks about a 100K model that it's using to represent these objects. So in this case, would they be having one model trained for pineapple and egg, or do they have a way of combining a pineapple model and an egg model?
It is an analog, sorry, not analog, it's the parallel model approach, and they would have to train that parallel model on both of those concepts, I believe.
Okay.
Cool.
Take a teddy bear and a teapot. Then ask this little AI to dress up the teddy bear and upgrade the teapot to have a cartoonish look. And now comes the magic. Let concept number 1, teddy bear, fuse with concept number 2, the teapot. And there we go. Wow! And that is not any teapot, that is exactly that teapot. The same objects can be reused. With this new paper, we can not only perform text-to-image, but we can build these little worlds exactly the way we want. This AI chef feels like it can cook anything. We can keep our characters and add our personal touch to them without losing these characters. They also provided a little taste test, a user study where a bunch of humans were asked which examples they liked best, and it came out that they not only liked this new perfusion technique the most. I have to say, I expected that at this point. But they also found something that I did not expect at all. Get this, the new personalized images were found to be almost indistinguishable in terms of quality from the original. Wow! And finally, number 4.
The comment versus indistinguishable versus the original was because the two approaches, as Ted pointed out in the chat here, the prior approaches to personalizing image generation degraded the quality of the outputs, either because it was fine tuning all of the layers, or because it was unable to accomplish full personalization because it was having to embed all the information in the Gaussian distribution as the input. And so what you're basically getting out of this paper that I think is really helpful, or sorry, this video, is you're getting a description of the limitations. One of these, the combination problem was really the limitation of the embedding problem, and then the fine tuning one has the problem of losing fidelity.
All this is done through rank 1 edits to the neural network. What is that? That is a proper surgical approach. This means that it introduces minimal changes to the neural activations of the neural network to achieve all of these changes, and that is likely why we are not losing out on the quality of the image. This is an incredible feat. Bravo, Nvidia! If you're looking for inexpensive cloud...
I thought this was pretty funny. These are my friends that sponsored this. I didn't realize that, but we'll turn that off now. If you don't know the guys at Lambda, they are actually pretty cool. All right. Any questions that we want to pause there, or can we go on to kind of a block diagram analysis of how this works? Okay, cool. I will move us to block diagram land.
If DALL-E or Midjourney doesn't ring any bell, then I don't really know what to do with you. You are already familiar with text-to-image models for sure, but you may also know that they are not really good when conditioned with images. Meaning that if you'd like to generate an image of yourself or include a specific object like a teddy bear in specific conditions, it might not work nearly as well. Those AI usually understand what you want and tries to generate new images, including something similar that you sent. But it's far from perfect, and you can often clearly see it is not the same object. Well, that's about to change with a new model from Nvidia, Perfusion. Perfusion is much better than all previous approaches at matching the generated results with the original image. So it's basically a stable diffusion with even more control over the output. Maintaining fidelity is extremely challenging for those generative models, while also allowing you to create new images in different contexts. So how do they do that? And what's the state of the art for finally generating tons of amazing images of yourself for your Instagram page without needing to go outside and actually take pictures? And how can we do that without having an immense model that only OpenAI can use? Because in their case, Perfusion is 5 orders of magnitude smaller than current state-of-the-art generative models like Stable Diffusion, which means its size is around 100 kilobytes. Seems like magic, right? Well, let's dive into that. But first, a word from a great company in this field. Today's video is brought to a concept seem to allow the count on. Look at that. The results are amazing, and they indeed seem to allow for much better control. This is what Perfusion is. When we say more control, we actually mean that the model is able to learn the concept of an object, animal, or person, and then generate these concepts in new scenarios. And for this video, I will assume you watched my videos on DALL-E and Stable Diffusion, and I will focus on the innovation of this approach rather than covering how it works from scratch. What's different here from Stable Diffusion, which they start from, is they add a new mechanism to allow the model to lock concepts like our teddy bear. They also add a way to give multiple concepts that can all be locked so that we can generate an image including multiple items we want, which can be quite cool for advertisement creation and many industries, leading to much better results both quantitatively and qualitatively than ever before when it comes to text-to-image generation with attached concepts. This is rather a complicated task since they need to optimize for two objectives: representing the concept accurately while also not overfitting on the image examples of the concept and allowing for personalization of the generated output. So basically, focusing the model's attention on only the concept and not the whole images sent. But how can we do that? Well, it's obviously by using a very similar diffusion architecture, but adding a few cool tricks to allow for a concept to be locked efficiently and reduce the model size with a technique called rank 1 model editing. So as we always see in the current text-to-image models based on diffusion, which look like this, there's always a text prompt that is encoded to extract relevant information. Then, this information is added one way or the other, usually through the cross-attention mechanism, to our image generation process, which is an iterative process as I explained in my diffusion video if you are not familiar with the model architecture. It's in this space with the cross-attention step that they worked. This rank 1 edit or
So this is the 100 kilobytes, by the way. This is the standard model, right? The standard LLM that you use to generate the DALL-E. And so you don't have a 100, again, just to be clear, you don't have a 100 kilobyte model. What you do have though is a 100 kilobyte, very quickly trained sub model down here that performs the actual personalization.
Space with the cross-attention step that they worked. This rank 1 edit or gated rank 1 edit here will help the model understand where the images are located in the final image as well as control what appears in this final image. So we have two objectives here, the where and the what, respectively represented by K and V. They are also using super categories instead of relying on the words themselves. So here, for example, they will edit the word to the super concept teddy, however we refer to it in the prompt. Like when we say its name Hugsy in this case, or any other synonym to say a teddy bear. The model will transform the encodings of the prompt to fit the encoding of teddy instead, so that the model always knows we are referring to it.
So this is how it solves that first problem. Just again as a reminder, there are two pieces of data that move from the left side of this model down here from the encoder into the diffusion model. The first is the key, the second is the value. The key is where, and the value is what. And what's interesting that they did first was that, and he's highlighting it here, is that they don't create an entirely new named entity. They attach the named concept to a prior concept. So this is Hugsy, which is an example of a teddy bear. And that, to go back to that prior video, that when I paused it here, this is a great example where the where is incorrect. The where that's getting customized to be Hugsy in this case is everywhere. And it's not being limited just to the area where I would normally put a teddy bear. And so it's getting personalized, but it's personalizing too many pixels essentially. And the first thing that this model does is in the where space, it says, I'm not going to put a picture of a picture of Hugsy anywhere that I wouldn't have been putting a picture of Teddy, which maintains the fidelity of the original underlying model. Now, if the underlying DALL-E model did make a regular teddy bear and broke it all over the place, then you'll still have that problem. It's not going to fix that problem of the underlying model. But what it does is it constrains the personalization of this named entity to that space that would normally be associated with the super class of it. Does that make sense?
On edit. This gated part comes from the fact that during training, weight updates of the model are only applied to the encoding components that match the concept. This gate is the reason why we can send it multiple concepts and it still works quite fine. It also allows us to regulate the strength of learned concepts, providing much more control than other approaches. And those are the only modifications they've done. Otherwise, it's the same stable diffusion architecture and the same principles tweaking the encoded prompts to better control the results. It's still not perfect, but a great step forward for text-to-image models with full control on the generation. Here, it will struggle with keeping the identity of the object we send it because of this step we covered where we refer to the object as a super category. which sometimes leads to overgeneralization since some supercategories are too broad and include many different objects or specific styles that we don't necessarily want here. They also mentioned that combining concepts requires lots of prompt engineering work, another reason to learn how to do better prompting. Still, the results are super impressive and the code will be available shortly. I'm excited to see how it will be used. I hope you've enjoyed this.
I'm going to pause one more time and go back here, because it's so if we this is one of the key or the key concept here, which is that we've locked the location based on what the super category. So you're not allowed to personalize the image, the output image, beyond the pixel scope of where I would have originally put a teddy. Now, what I am allowed to do is basically with reasonably open neural network nonlinearity, I am able to modify anything within that space, though, and that's really kind of you kind of constrain where, but what you put there is pretty unbounded. And so that's a high level overview. I'll go into some more detail on the paper, unless people have questions so far. Okay. So these two things we kind of covered in the video. Obviously, there are 2 or 3 other key concepts that I think are worth discussing here. The first one is, how does it do these things? And Rome, the rank 1 editing, is really the moving part here. So it's not just that these blocks exist, it's that the way that they are trained uses this rank 1 editing technique. And the reason that's important is because one of the key problems that we have here, I already talked about kind of the attention overfitting, where we need to make sure that we're constraining where the heat map, and this is in the paper in quite a bit of detail, where it is that we're putting our attention. But then once we do that, doing this Rome rank 1 editing is modulated somewhat. So at this juncture, I would ask for a 5-second or whatever update to what Rome is from somebody more educated than myself, and then I'll talk about some of the modulations they made to Rome in the context of this paper.
All right, I'll take a stab at that. So in the Rome paper, this was just a language model, so there's none of this image stuff. And they simply said, can we figure out where in the model it stores a certain fact, like the Space Needle is located in Seattle? All right. And they tried to do it, and they did some counterfactual analysis, blah, blah, blah. But then they said, well, how can I prove to you that that really is where the fact that it's in Seattle is stored? Well, I know if I overwrite those numbers and it changes it to say the Space Needle is located in Rome, then you will, or Paris, whatever, then you will know that I successfully found the right place. Okay. So then they asked themselves, well, how would I actually go about doing this? And so at the end of the day, they picked a feed-forward network, part of the big transformer giant neural network. And if you're familiar with just regular MLP feed-forward networks, their weights are just square, matrices, right? Like inputs by outputs inside rectangular, but in this case, like square. And so rank 1, if you know your linear algebra, right, it's just it's sort of like how many basis vectors you can find in the row or column vectors of a matrix. So by saying rank 1, what we mean is a very simple matrix. So if you took a column vector, so let's say you had a 100 by 100 matrix. If you take a single 100 length column vector, multiply by it a 100 length row vector, you will get a 100 by 100 square matrix, but every single row is going to be a multiple of the first row. They're all just multiples of that. So it's not actually a fully complicated matrix. It's much simpler. So by doing rank 1, they're constraining how much they can change. So long story short, they limited their edit of this square matrix to a rank 1 edit, a much simpler edit, because they don't want to dramatically change it. They just want to surgically change it. Now the question is, how do I know what the input to that matrix, the matrix multiply, the parameters, is going to be that I want to change? And how do I know what's the output that I want it to change to? So they addressed both of those questions in the paper, okay? If you think about a transformer, you'll know that, like, the word, whatever, dog, has a specific embedding, okay? So if the embedding dimension of the transformer is 1024, when you input the token dog, you're going to get always this exact same vector of 1024 floating point numbers. That's at the very first stage of the model. But they were editing something that was halfway up in all the layers of the model. So now the word dog is no longer going to be identical by the time it's made it halfway through your language model. And so depending on what the previous words were in the sentence, you're going to get slightly different things. So on the input side, they said, okay,
where this comes in. Sorry, I was trying to just show I think the key graphic I always try to remember when I think of Rome is this one, which is where is the actual space needle, right? And what it's basically saying is that the space needle's around layer 16, in this one. And so when we're doing our rank 1 edit, we can focus essentially there.
Yep. So if you're looking for the word teddy or dog or whatever, what they did is they just had a whole bunch of sentences that had that word, and then they averaged what it looked like by the time it got to that particular point. Okay. So they're going to do something similar in this paper, where if you read the paper, you see I star. They've averaged what something like teddy looks like by the time it gets to that point. The process on what you want it to turn into is a little bit more complicated, but it's sort of the same idea that you can see sentences that have the word Paris in it and sort of mathematically work your way back to say, this is the set of numbers that I want. And so then once you do that, then there's a small amount of math needed to say, how do I do a limited update, a rank 1 update of this matrix, such that if you multiply the input I star by this, you get something that looks more like O star, the output average that we want, instead of whatever it used to be. And so net, that's sound like a little hand-wavy.
And uniquely, I think with Rome versus the prior approaches, what was neat about it was that while it was rank 1, which is kind of, might be considered naive, its ability to not only execute these changes, but to execute these changes in a way that truly represented and captured and updated the entity. So then if you asked, how far is I think the example is how far is the Eiffel Tower from Pike's Place Market, it would know that now it's in downtown Seattle. So therefore it's like 1.5 miles away instead of, 20 or 15,000 miles away, right? And yet it also didn't modify everything else in Paris. And so it's similar. What's interesting about Rome is you're doing a similar thing. You're editing it, but you're also constraining the scope. You need to keep the precision high, but not expand the scope such that you're vomiting kind of all over the rest of your data and losing all of your other data.
Right. So in medicine, we say sensitivity and specificity. Okay. So if you're trying to change the space needle, you want it to change the space needle to be in Paris, no matter what sentence it is, no matter whether space needle's early in the sentence, late in the sentence, whether you talk about this, that, whatever, you want it to work in every sentence. But you don't want any other building to have changed its location. That's the specificity. Okay. So they showed in that paper that they had very good sensitivity and specificity. So I think the authors of this paper said, so if this technique has really good sensitivity and specificity, then if I want Hugsy to change from whatever the default output is to always output what Teddy Bear on average outputs, but I don't want anything else to change, this sounds like the same exact problem that the Rome people solved.
That's exactly right. Now they did run into some specific things that Rome wasn't able to resolve, and I got a little lost in the math there. It sounds like, Ted, you read this paper. there's a couple qualifications and modifications they made to Rome. The one that I got that I love, I'll talk about, and then if you want to help me with the next one, the one that I love was they're able to search the entire Pareto manifold essentially, and so they use this single, they use a bias term that basically goes from are we keeping the sentence, we're biasing towards the sentence, the text, or are we biasing towards the personalization, meaning that I'm going to literally kind of photocopy parts of this image in here. So if the bias were 0, theoretically you'd end up with one of these 2 images, right? Whereas if the bias were 1, you'd end up with the superclass placed in this without any personalization. In this example here, you've got this cat statue thing. And so at a very high bias, you end up with something that has some of the colors and some of this, but it maintains the stylistically true statement, which looks like it's a Monet. And then when you lower the bias, you'll lose parts of the Monet-esque elements of it. And it uses some sort of a non-linear attenuation, it sounds like, to apply the personalization from Rome. That was, correct me if I'm wrong, but my understanding was it essentially applies this hyper nonlinear attenuation to the ability for Rome to edit those nodules at inference time, which was pretty cool.
Yeah, so if you crank things up too much, then from that original teddy bear that you use as an input, you'll get a teddy bear that looks just like it, but also like in the exact same pose. Like, you don't want the teddy bear to look like that if it's riding a bike. You want its arms to be in a different position. And so you have to find this balance between, I want to super strongly tell it to follow my instructions that teddy bear should look like this, but I need to also back off and not tell it too strongly, or else it'll just be stuck with like an exact copy paste of the teddy bear. I need it to still semantically do, you know, other things. So how can I get the best of both those worlds and have the entire rest of the image, the bicycle, the thing that's supposed to be behind it, the thing that is supposed to be holding, to have none of them get affected by my putting my thumb on the scale to say the teddy bear should look like this. And so there's this dot product that happens in the Rome paper to see whether or not in that case, it's only tokens, it's words, to see whether the word is Space Needle, the one you care about, or not. And they said, okay, that kind of works, but you can have dot products that are sort of similar if the word's not exactly the same. So we're just going to crank these things up. So if you're familiar with the sigmoid function that's used in logistic regression, we're going to apply a sigmoid on top of that dot product to say that, and this is where you need the thresholds, the bias and the temperature. To basically say, now it's this sharp S shape instead of a linear shape, where if you're below this value, I'm going to push your number towards 0. Don't pay attention to this. And if you're above this number, I'm going to push your number to 1, saying, pay super, super attention to this. And so that's all that they really did, was just sort of take the already pay attention thing and make it much more of a binary on-off kind of a thing, as opposed to a gradual thing.
And again, I think what's interesting about it is that in the exploration of the Pareto, you can see kind of those mechanisms in place in the examples that they provide. So I think with that, I'm actually getting to the end of my prepared content. If anybody has questions, happy to do that. Otherwise, I can kind of summarize. So again, at a high level, I think that I tried to come up with a positive sentence about what it does do. I think that Perfusion does accomplish this personalization and find balance between personalization and high quality images. I can't verify it's 5 orders of magnitude because they didn't release the code or the data. But let's call it 5 orders of magnitude smaller. What it certainly is, though, is the other 2 methodologies, and we didn't go into this in too much, but the other 2 methodologies, which either fully affect the embedding or fully retrain the entire diffusion network, require a ton more computation and computational memory updates. So because you're only operating in this tiny 100K space, yes, you have to have this, yes, you have to have this, but you're not updating all these parameters. In a space where you're updating the entire network, you're updating, again, billions and billions of parameters. In the space where you're updating the embedding, you're also updating the billions of parameters that go into the embedding space. And so I would certainly, based on what they're reporting, I would support that it is a massive computational leap forward, though not actually a 100K model. And I would also verify in reading it that one of the things I do like is that this effectively uses the parallel model approach. You have a model kind of sitting alongside your major model, which was aligned with what Roger was presenting over the last couple of weeks as well, which is that we're finding increasingly, as the core models get bigger, that finding additional ways to compute and update parameters is increasingly important. And I think one of the neat things that Roger presented, was it Roger or you, Ted, was that training speed and efficiency ultimately also result in more capability, which is, I think, immediately manifest in this paper. You're able to do stuff that you weren't able to do before because you're really focusing your training effort on such a smaller set of data and a smaller set of parameters. And so therefore your output can be significantly better. You can do a lot more training with it. It does still rely on the large language models. It does add these two key computational blocks, the key locking and the gated rank 1 update. It does also, another thing that I really like is a concept that's become increasingly popular over the last few years is few shot or one-shot learning. They have examples of one-shot, few shot. I think they even had a 0-shot learning example in the paper, if I'm not mistaken. And I think that's also really neat because few shot really pushes us to the limits of generalization versus bias. How do we find, I don't want to say semantically meaningful, but human interpretably meaningful balance between generalizable and personalizable. And the fact that we're finding increasingly good ways to do that, I think Rome was the paper that really jumped out at me, was we're able to isolate the concept that we're updating. When we moved the Eiffel Tower, we didn't remove the rest of Paris. That to me really tells me that somewhere in these models, we're finding actual concepts and concepts that are psychologically aligned with the way human beings think about those concepts, which is the word semantic. And then I really love the Pareto manifold exploration. The examples they show of this, this is just phenomenal to me. I mean, I think the rest of it's cool too, but this really shows how robust the underlying model is to pushing. You can actually visually see, I can push the bias this way, and I can push the bias this way without losing fidelity, right? And so the fact that we're staying kind of pretty close, this is obviously isn't a manifold, this is a line in this case, but in the space of images, we're kind of exploring this manifold, which is maintaining an image that is true to both the constraint of personalization and true to the constraint of the text to image problem. And yes, you're doing the trade-off between the two, but you're never pushing one all the way away. You're actually able to fully explore the entire manifold. I thought that was probably one of the most impressive results because it indicates the robustness of the underlying model. So any other questions? Otherwise we can pause and go to agenda.
Just that last diagram that you're showing, yeah. I thought it was really cool too. And I didn't look, I don't know if there's anything in the appendix, but I would have loved to have seen them show what it looks like if you pick a really extreme bias, like 0.05 or 0.95, because like they showed like reasonable images, like the app icon that's supposed to be dog, right? The one on the far right isn't what you want because it just looks too much like a dog. It's supposed to be an icon, so it's not following your text instructions, right? But it would be interesting to see, because if you go too hard, then you're going to have a problem, because it's going to be very icon-y, but not doggy enough. And then in the other extreme, it's going to be like, isn't that just a copy paste of the dog? like no change in pose, no nothing, just like you just pasted it into, you know, this little box or something like that. Like, it would have been nice to see those really far extremes too.
Yeah, I mean, you're always looking for like, where does it fall over, right? Well, again, I just thought it was so impressive that it had such a broad range at all. Every other model that we've kind of seen at this stage of maturity typically kind of falls over pretty quickly, you know, as you move towards the extremes. But yeah, I mean, it would be interesting to kind of, it would elucidate something about the underlying mechanics a little bit. And the way it fell apart was it exploded back into noise, or, you know, yeah.
Yeah,
Who
did you
knows?
just get garbage? You got a, you know, a 17-leg dog, or did you just get like I was saying, a copy paste of your original? Like what is the thing that, you know, breaks down if you go too far? But overall, yeah, I think the paper is really strong, and just like I think the authors said it in their conclusion discussion section at the end or whatever, but just note that you definitely have to, as the user, pick what's the right super category. So like, you want to pick a super category that has the right real world implications. So like the teddy bear, if you had said doll or toy or whatever, you might have gotten different things in terms of like whether or not the arms are expected to be able to move, or whether whatever, right?
It's fully key locked, right? Again, it's fully key locked.
Yeah, because it's locked. You want to pick the one that has the right physics for what you want to be able to change, what you don't want to be able to change. And then the other thing is, I'm not sure, they showed like the Pareto front thing, you know, I'm not sure at the end, they didn't seem to say like, so we recommend that you use 0.75. It sounded like you might need to, for your use case, experiment with like 0.8, 0.75, 0.7.
They talked about that in the appendix a little bit. So they talked about effectively kind of the with the qualitative tests, especially, that they use these different bias numbers in the qualitative tests. And that the conclusion is what you said, is that each use case is different, but that again, their kind of strong claim was that in all values of the bias that were kind of in that middle, you know, not 0.9999 and not 0, that this model far outperformed all the other models.
Yeah, I'm not dinging them for it. I'm just saying that, again, like, just being realistic, it's not like if you were to put this into Photoshop, I think that their bar would be a little higher, that they don't want the user to have to fiddle with a knob to get it to work right. They're hoping it'll just magically work right the first try.
Yep, fair enough. Yeah. All right, any other questions, comments?